wanted to talk today about transitioning from verification to validation to the digital twin. Now, what I find really interesting over the last few years is if you look out into the market where certainly 5-10 years ago, semiconductor, it always felt like we were a little bit on the edge of the overall economic domain. Things like energy and automotive, they were all very, very important industries, and semiconductor was kind of this high-tech outgrowth on the side. Well, if you look at the business press these days, you can't open one up without seeing someone talking about digitalization, digital world, digital enterprise, the digitalization of everything. And I think that that's all occurring because people are really looking to leverage semiconductor technology to change their business model, change the way they handle logistics, change the way they handle finance. Everything is going and becoming part of this new environment that we're creating, and it's driving an incredible opportunity for our semiconductor landscape. One of the easiest ways to see this is to take a look at the forecasting for data. What we're looking at here is a 400x increase over the next few years. That's 92% per year. And you can see whether the end market is around gaming, video, IoT, medical, all of those markets are projected to be larger than the entire data traffic in the market today in those out years. It's an amazing opportunity because that data needs to be processed, it needs to be transmitted, and it'll all be done so in semiconductors. You can also see it in the storage market. 16% CAGR per year to try to manage the storage of that data, mostly being driven off of new types of storage devices. COVID, if anything, has accelerated that trend. When we first went into lockdown, consumer companies like Zoom became incredibly popular as people tried to maintain their connections with their friends and family. But what you've seen since then is the whole aspect of having to do work from home and us all working with closed offices has driven an explosive increase in the demand for business applications to support that collaboration. And this is something that I don't see going away, even were we to end up with a solved crisis in a few months. And that's because it's really illustrated people's ability to work in a new way. And most companies are now talking about a new way of working going forward, which includes far more flexibility for employees, more of an ability to work from home or a remote location, with then the office really focusing as a real-time, more informal collaboration environment. And thus these trend lines have, if nothing else, been accelerated during this crisis. So it's an immense opportunity moving forward, but it's going to bring new requirements to our designs. They're going to be driven by those business workloads and demand a level of energy efficiency that we really haven't seen before. And so on the workload side, whether it's the tie-in, again, from an autonomous vehicle into a smart city application, whether it's an IoT application that's managing factories globally, it's that workload and how it works with the semiconductor that's going to define success. On the SoC side of things, we'll continue to have multiple CPU cores. We'll continue to have all those wired and wireless interfaces, memory management. But what's going to be really important there is the addition of accelerators, whether those be video accelerators, machine learning. Those are the things that are going to be able to deliver that increased energy efficiency that's going to be necessary to meet the market need. And driving up and down that stack will be a continuity of the use of AI. Some time ago, back in the early eras of the internet, Mark Andreessen made a comment that has since been used quite often. It can be seen as being pretty prescient, and that is software is eating the world. And what I think is key to understanding the rest of what we're going to talk about is that there is a somewhat less poetic, more prosaic corollary to that. And that is software performance is going to define semiconductor success. And so if we look at this, we've just talked about an incredible opportunity, but it is also a complex problem that needs to be solved. But that complexity can be an opportunity rather than a threat. So think about something like an autonomous vehicle. In the end, the OEM is bringing together multiple CPUs, multiple electronic systems, integrating that in with their drivetrain, braking system, chassis dynamics, all feeding out from the outside world. And what we need to do is validate that works as a systems test in the end in the lab. That's an opportunity for incredible delay. If we can take that environment, shift it left such that we can bring this all together in that digital twin to be able to both validate and test and determine performance characteristics of designs, we're going to be able to be far more successful in the market and have much easier transitions into these new environments. So when we say digital twin, I think it's important to step back for a second, because I know when we first started talking about digital twin, in many ways, people's reactions were fairly common, including my own, I will admit. And that is that ICs have had digital twins for 25 years. We simulate designs all the time. We create a digital twin of the design. And that's certainly a part of what enables a digital twin. But I think it's important to realize that the vision goes beyond that. What the vision goes into, there's not just a digital twin of the design that you can simulate. There's also a digital twin of the manufacturing process, and there's a digital twin of the device itself being utilized, and that those are all tied together in a way that allows us to do feedback continuous improvement from the downstream parts of this and feed insights forward. So for example, one of the visions there is that when the device is actually operating out in the field, issues that occur can have their data captured, fed back, and have a matching design digital twin that can then look and determine ways of perhaps being able to do a field upgrade or mitigate the issue in future designs. So three things we'll talk about, three main areas in how we see this playing out for the IC designer. First off is SoC creation. We think there's going to be a new usage of tools in that area that can help us with this particularly important issue of architectural exploration and how it will affect power and performance. There's the issue of SoC verification as well, where here, as we talked about in the title, we're really looking at things going from verification of did I meet spec, validation that I can run my software stack, to digital twin that I can manage the validation of that chip operating in a full environment in a real world context. And then finally, there's the aspect I just talked about a second ago, which is how we can put in place the environment, technology, and tools that will allow us to take information off the SoC when it's in its utilization cycle and use that to further increase our insights into the design and operation. So on the design creation side of things, really a key factor here, you can't talk about energy enough. We just do a simple math issue. Right now, the estimates I've seen are somewhere in that 1% or so of global electrical capacity is being used to drive data centers. Now, if we talk about the amount of data being transmitted, stored, processed, going up by a factor of 400, that causes an obvious problem without a significant increase in energy efficiency around managing that data. And you can see that in some of the market studies that have been coming out, where it talks about the amount of the market that will be done and achieved with tools that have very low power usage is one of the biggest opportunities, but that low power usage will still require fairly high levels of overall processing speed, and that needs to be managed architecturally. We think the most important part about being able to meet that challenge we just talked about is really being able to worry about architectural issue design rather than the detailed design itself. Here, by utilizing high-level synthesis, being able to design at the C++ system C level, we're able to concentrate on how that architecture will be performing against the application that's being loaded on. We can explore out the aspects of how we do memory, how we do bit lengths, how we do encoding, how we do the depth of the neural network, all of which can be quickly changed within the C environment, run then with the application, and then look at the overall performance, and then use the synthesis to automatically drive that down into a hardware implementation once we found that sweet spot, delivering the best performance at the lowest energy. And we've been able to prove this out over multiple years now, where people are able to achieve acceleration that well outpaces what's being able to be done on a software implementation on top of a CPU. as well as being able to do so with performance that meets or exceeds hand-coded RTL. Let's look about the verification side a little bit now. Now, this is an area that has been trending for quite some time, where verification that did I meet spec is important, but validation is more important, that it can actually run software. Here, whether you're talking about managing various CPU systems and how they're going to be handling the cache coherency across multiple applications running at the same time, design specific subsegments that need to be managed and integrated in with those, how we handle memory and interconnect, what happens with safety and security, what is the power and performance, all of those become important parts of our overall validation stack that needs to occur on these designs. This is incredibly challenging when we add on top of that now that we need to be able to manage what is going to be the actual performance executing on software. That becomes the key issue. And here what we're looking at is achieving another level of shift left to be able to take and provide an environment where you can take different parts of design at different stages of the maturity cycle, bring those together, and be able to run software much earlier in the design process, enabling you to ensure that when you deliver into these complex systems, they can still execute as necessary to make you successful into the market. So let's step back for a second and talk about what this environment needs to look like. First off is that we need to be able to handle and enable the presence of customer workloads. And so whether those be industry standard benchmarks that need to be met, specific applications that are germane to your implementation, or things like graphics testing and the like. That then needs to be able to be fed into a easily configurable system that can handle being able to bring together virtual models for a CPU, a gate level implementation for perhaps an accelerator, and perhaps RTL for a memory subsystem management tool, and then swap in and out depending upon the maturity of those parts of the design in a quick manner. We need to also then have the engines that can sit underneath of that configuration, running things like CPU models, running simulations on a standard type of netlist, and bringing in the hardware-assisted verification tools like emulation and prototyping to get the amount of cycles through design necessary to be able to validate full software stacks. Now, once that's all running, what's needed on the other side are analytics tools. Tools that can enable you to focus in and understand the effect of the application on things like power and performance, and then an environment that ties that together where you can have a single environment that is managing both software debug and hardware debug so that you can pinpoint the issues that are causing the misses against your performance specs out of the analytics engines we just talked about. Now, what's this look like in the end? Well, it's a system that enables us to pull together these benchmark frameworks, run them against real designs, some of which will be, again, virtual models running on a CPU. Others will be on emulators or prototyping types of environments, and be able to then put on the analytics where you can see here there's a section running that's showing the power driving in various subsystems of the chip based upon the workload of the graphics execution that's occurring there, all of which is tied into that software debug environment. Now, that trend in terms of moving to where you can do software validation as well as just verification has been going on for a while and is accelerating now. But I think really what takes it to the next level is when you tie in then the digitalization of the environment itself. A great example of this is PAVE 360. We announced this a while back. PAVE 360 is a digital twin environment focused on enabling automotive autonomous applications. So sitting in the center is that validation environment we just talked about, where we can bring together multiple chips, different levels of maturity stage, have them all operating together, processing data, and producing outcomes for the vehicle. We also then have added on top of that the ability to tie in these virtualized real-world environments. So on the left-hand side, what you can see there is a system that enables us to model a real-world road, whether that include other drivers, pedestrians, traffic, lighting, traffic control systems, That data can then be fed into the virtual sensors for the device, fed into the electronic system, and then used to control models of both the powertrain and the chassis, feeding that back then into virtualized environment so that we can actually run a complete virtualized environment with the semiconductors operating well before that anyone has ever even thought about pushing the tape out button to go to silicon. That's a true shift left environment and enables the OEM to get a level of confidence about the decisions they're making in terms of chips that is completely unprecedented. And the digital twin is not just useful in areas like automotive and autonomous driving. For example, in 5G, what we're looking to do is to leverage the technology we have available today that can model the electronics behavior on the edge and at the cell tower itself, and combine that together with models of the channel, the types of degradations you can get by the actual transmission through the air, as well as the interface up into the cloud so that then we can model out that entire stack again and look at how these 5G applications will perform, and more specifically, target your designs such that they perform in an optimal way and can capture the most market share as we attack this opportunity. Now, I talked a little about it's not just being able to simulate a design. It's not just being able to wrap in this external world environment. It's also being able to really tie this all together by looking at how we can take the device when it's in the field and pull its data back into this whole digital twin environment as well. Here, what we're looking at is leveraging the technology that we've been using for a while in design for test. If you think about design for test, what are you doing there? Well, one, you're analyzing a design, and then you augment that design with IP that allows you to more effectively do structural test. And so because we do that with things like compression and scan, we can take these 100 billion device chips and test them in very short time frames to determine whether or not any of those billion devices is not working. We've also been leveraging that same technology into the realize aspect, into the manufacturing aspect, where because we get such precise data around individual elements of that design, we can also tie that back through diagnostics to yield learning that can show where there's design process integration issues, where a certain pattern might be causing a via voiding that's causing systematic defects that will lower yield. We've also been leveraging that same thing with structural test to do some basics around in-system tests for things like autonomous vehicle and safety critical applications, where the device itself will, while operating, run cycles to determine whether or not there's been a structural failure and whether or not that particular device needs to be taken out of operation. But moving forward, there's an even more exciting set of capabilities we can bring to bear. Here, what we're looking at is doing functional monitoring. So it's that same aspect of analyzing the design, adding in IP that will then do functional monitoring, whether it be about individual circuit elements, buses, external interfaces, or internal, and then be able to do analytics and monitoring in real time as the device is in operation. And so what's going to be possible with this type of technology? Well, it ranges from basics like doing bus monitoring to do something like detecting a stuck pixel that may be affecting the overall ability to process imaging data as it's coming into the system. It could be something like looking at thread switching and out-of-bounds execution where a Trojan or some other types of attack is coming onto the chip that can be detected by watching what's happening with the address bus on top of the CPU. Or more sophisticated tools like being able to bring out that data, feed it up into the cloud, and being able to run machine learning-based detection to look at more subtle types of issues that may occur, whether those be from a reliability or from a data integrity perspective. So if we go back, we think we have a really exciting opportunity moving forward. Truly, the world is going to be relying upon the innovations and technologies that the semiconductor industry can bring over the next few years. We think there's an opportunity to take that complexity that's going to occur because of what we're going to be trying to implementing and turning that into an advantage for us all in terms of enabling this digital twin, giving better insights and better designs over time to be more successful in the market. So I want to thank you for your attention, for staying with us this year. I want to thank you for all the energy you put into this conference. Really looking forward to watching the videos, and even more, I'm looking forward to being able to see you all in person soon. So thank you.